It's not recording.
And we are.
Now it's recording.
And I told you.
Now it's recording. Hello everyone, this is lecture 20 of PTRE 465531. Our TA is grading the exams. I think the last one was submitted last night, so he should be able. I would be having a feedback to you in regards to grades as soon as I can. Anyway, last time we finished module two, which was quite stressful for many of you. It was like very mathematical intensive from my understanding. Then today we will start, it will be a short lecture today. We are gonna start the module three. No, it was me, up to my. Module three is more applied rock failure mechanisms. So we did talk about, in module one, we talked about boundary conditions, externally applying boundary conditions. Module two, we talk about stress deformation behavior of the material. In module three, we're going to talk about failure. Okay, when do I have failure and what kind of failure do I have? We introduced this topic in module one when we talked about mode one failure. And you saw that on the exam too. We talked about tensile failures, cracks. So it's like opening, taking the chopsticks, flipping them upside down and opening them apart. Yeah, tensile, mode one failure. Yeah. Those are hydraulic fractures, basically. What we do to stimulate the rock. But there is two more kinds of modes of fracture, which are shear. Like in-plane shear, which is mode two, and sliding mode, like this. And then you have the twisting mode, which is mode three. Now, in real life, you never have a single mode of fracture. You have a little bit of all of them. It's a combination of all three of them, but one kind may be very small, you know? For instance, when you have strike slip faulting, the edges are basically mode three. Hydraulic fracturing, it's mode one, but on the walls of the fractures, you have mode two. That's why we use microseismic to monitor hydraulic fracture jobs, because microseismic does not detect mode one, it detects mode two. So if hydraulic fractures are mode one, why do we use microseismic? The truth is that you get a lot of mode two on the walls of the fracture. Yeah. And this is what those microseismic signals are detecting. Yeah, that's the only thing that it can detect, basically. Earthquakes are mode two. And we're gonna talk a lot about shear in this module. We already talked a lot about mode one, but let me, say again what I said. The way the fractures open is probably the most, the way mode one fractures open is probably the most important concept of this class. So we talked about it in module one. You may see it again. It's pretty important to be comfortable knowing how mode one fractures open and the direction they take, the plane of propagation, etc., etc. Sliding mode is mode two. That's the common earthquakes. Tearing mode, also earthquakes, but more like strike slip faulting moves. Yeah. So those are the fracture modes, and this is basically, it's universal. It's not applicable to geomechanics only. Geomechanics is like this kind of fractures in rocks, but you can have it like in any kind of solid equipment, right? Anyway, so three types of rock failure that we can have. Rock yield is basically failure induced by tensile stresses. Sorry, that wasn't. Imagine I have a rock and I pull it apart, I tear it apart, and it will break somewhere here. It will be a tensile failure, right? It's pretty simple because I have the rock grains held together, and I'm pulling them apart, and I need to break this bond, and with the orange stress, and I get failure. So we have to beat or exceed the tensile failure criterion of the rock to get tensile fractures. And we're going to talk about it later, but for that to happen, we sort of introduced it before, is basically this. T is the tensile strength of the rock, okay? What holds the rock together against tension. And then sigma 3 is the least compressive stress applied to the rock, i.e. the most tensile, right? Least compressive, most tensile. So for this to happen, if I have a stress in the rock that becomes more tensile than the tensile stress of the rock, and I'm using negative here because it's a negative, it's a tension, so it's negative in this class. Tensions are negative. Then we have mode 1 tensile fracture. Okay, pretty simple, quite simple criteria, and we are going to elaborate on that later in this module. But what about another kind of fracture? Shear failure. Shear failure in general, it's going to be a slanted angle, and there is a reason for that, and why this angle is about 16 degrees from the horizontal. There is very, very important reasons for that, but generally for shear, it's not a very simple criterion like the orange one for tensile.
20 degrees from the stress, principal stress.
Yeah, to get shear stress, to get shear failure, you have basically, let me show you two stresses that you are dealing with. You have the stress that holds these two pieces of rock together. That's not a good color to use for the white. Okay, very nice. Okay, you have sigma n. That's the normal stress that holds these two pieces of rock, let's say, together from breaking apart. And then you have the tau, yeah, the tau in Greek is basically the shear stress. But the shear stress is not a product of one stress. It's not like a directly applied stress. It's a product of two different stresses. In this case, is the compression I apply on the axis of the core, and the confinement I have on the outside. Yeah. So I need to consider this and this. Oops, sorry. To get to basically calculate tau. Tau is given to me by an expression or that involves two or more stresses. It's a function of tau is a function of the let's just call it axial stress and then confining stress.
Yeah, when you have the sign here, right? Like what sign? The angle.
Yeah, the angle.
Here we have it in the function.
Yeah, it's an angle. It's always 60 for rocks. Around 60 for
So
shear
the horizontal.
Yeah.
Mostly 30 degrees from the main
From
stress.
Yeah.
From the stress, we will have a plan with like 30 degrees with.
Yeah, 30 degrees right, sort
Yeah.
of deep, sort of. Yeah.
And then when you reverse it, you will see the same thing.
Yeah.
That's how they identify the regime stress in the field. If it's
like you have, for example, a compression,
Yeah.
you will have more faults with 30-degree angle, 45, 30, something like that. If it's like extensive regime, you will have more fault with 60 degrees, which is normal stress.
Normal stress,
Yeah,
yeah.
that's how they, paleo stresses, like when they globe up everything with faults, like they call it like brittle deformation in the basin, they go with these angles.
Yeah.
They don't define what.
Even in drilling, the cutting rate of the rock is like this. It's like at this degrees. Yeah. And
So is that the angle fee?
the angle fee? No, the angle fee is basically what Malek is talking about. Is this?
What that is the 30 degree.
Yeah, but it's the angle of the plane, right?
It's like this angle,
Yes.
the angle from the horizontal.
Degrees, yeah.
Yeah, and then you can do it from the vertical though. What Malek was talking about this degree. And then you have basically something like that. Yeah, 60, 30, they make 90.
They tried all the materials in the lab to prove that these angles. They tried in quartz, feldspar, igneous rocks.
It's
and-
mostly the same.
Yeah, they found the same like 30 to 45 max.
And this would be 90.
Yeah.
Yeah,
And some shales in Gulf of Mexico, they have 80.
no,
It is, in Zobot, one of Zobot's field.
because of clays.
Yeah.
But it's not shear failure, right?
Maybe extensive, like,
I'm talking about the angle. It's up to 82 degree.
Yeah, but what kind of failure?
what kind of.
It must be tensile
Faults?
failure.
Also, what?
No, you know, when we, for a specific approach, we have Poisson's ratio and we go, and then we have the fee. So theta is, and then
Oh, that's a different fee. That's a different fee. That's the tangent of the, it's similar but not the same thing. It's related. That's the tangent of the mu, or arctan of mu.
We are not talking about this one.
That's the friction
not
of
the
the
same.
faults. That's the friction of the faults. It's not the same.
Not the same.
It's not the same, yeah. But we use phi for this as well.
Yeah, you have here and theta, both.
Yeah.
There is another fee.
There is a different kind of, that has to do with the friction of the fault. So imagine if this fault is moving, the friction only is 0.6. So it's related, but it's not, yeah, actually it's related very much. I don't know if 82 is pretty high, but yeah, anyway. So this is how you find tau. You need to basically calculate tau, and then that depends on two stresses, right? Compare it with sigma and the normal stress holding the rock together at 90 degrees to the rock, to the fault. And then if you have if your tau is big enough to beat the normal stress, then you have slippage. Okay, you have failure. The other failure that we are not really going to talk about much in this class is compressive. We won't talk about it too much in this class because it's a little bit rare for our. Look at how this goes. Does it become smaller? There you go. Ooh. Become smaller, and that's compressive stress, compressive failure, or a failure caused by compressive stresses or confining stresses. That's how we measure also the bulk modulus, or we learn how to measure the bulk modulus. And of course, just like with the three modes of fraction, I cannot have a pure tensile failure. I cannot have a pure shear failure. I cannot have a pure compressive failure. I'm always having a combination of the three, but it may be that one or two times are tremendously dominating. Rock damage can be explored separately, of course, for each failure. Now, tensile failure is not new for you, okay? It's we have already talked about it. Application of tensile stresses with negative sign according to our geomechanics convention on a metal bar results in tensile strains, which should also be negative. So you apply tensile, imagine, and this is a hypothetical case. It's not easy with rocks, but imagine I have this rock bar. I'm applying tension. So my stress is basically negative because it's tension. And then eventually I'm gonna have failure like this at 90 degrees, roughly 90 degrees. And we're gonna talk about that later on in this module. I pull it apart until it breaks. I cannot really do that with rocks, so I'm gonna use a different kind of test process for tensile failure, but that's the idea. Okay, if I have a negative sigma 3, my epsilons will also be negative, right? I'm trying to elongate, right? I'm elongating this. So it should be negative, right? Epsilon strain is negative by our convention. If you use a different textbook that is not for geomechanics, that is for, I don't know, solid mechanics, it may be the opposite. It has positive for tension. The maximum tensile stress of a solid that the solid can handle without breaking is called the tensile strength. We call that T. We abbreviate that with T. Metals are usually ductile and deform after reaching a peak stress. When unstressed, the solid does not recover its original length, but remains with plastic deformation. This is metals. The rocks are more brittle. They are like glass. 1D tensile strength test for metals, which is very common in mechanical engineering, is not easy to implement in rocks. You will have to grab the rock on its side or glue its ends, and try to pull it apart. It won't be easy to do in the lab. Okay, we're going to do something else in the lab for the rocks. And also bear in mind that where you grab the rock to pull it apart, where you grab it, it might break, right? So big issues using that. It's easier to do that with metal. Very common in mechanical engineering and industrial engineering, actually. One alternative is to machine the rock to a convenient shape so that you can pull it without using glues or grabbing jaws. However, rocks are not easy to machine. Rock failure in simple tension usually displays brittle failure, like glass. It falls down, brittle, right? Boom. That's how the rock is. Glass is sand, right?
It's quartz.
Yeah. It's quartz. No plastic strains follow after reaching the T. So once you exceed T or minus T, you have failure. End of story. Okay, you have fracture initiation. That's why Nassim, my undergraduate student who's working on fracture initiation, he writes models that they check whether T is exceeded. And after that, those models are no longer valid because you have created a fracture. Then if you want to create a model for, say, fracture propagation, you need to be able to have your model incorporate the discontinuity in the system that is the fracture. That's why we say fracture initiation is not the same as fracture modeling, like fracture growth modeling or propagation modeling. Typical values of tensile strength for well-cemented sedimentary rocks range from 70 to 1500 psi. To give you an idea, gypsum plaster or plaster of Paris is 294 psi. Hydrostone cement, which is similar to Portland cement, is 700 PSI. The biggest value I have ever seen for tensile strength of the rock under severe confinement, and almost for shale actually, it was from a Japanese paper I read from 2015. It said like it was approaching 2000. That was crazy amount. That's crazy high. But this range is sort of what you expect. And I would say closer to 70 than 1500. Now, uncemented sediments like loose sand, common in sedimentary basins, I mean, you don't need to pull them apart like it's basically, you don't have any. I don't know if this is realistic to say that T equals 0, but they act as if T is equal to 0, right?
So in the far field,
Yeah.
T equals sigma 3, right?
Yeah. I don't have a presence of a well or interference from other stuff. So this is tensile failure, right? It's like,
Yeah.
okay. When I apply T is the how much strength I need to do this tensile failure, let's say.
So in the far field, it's sigma 3,
Yeah. Everywhere is sigma 3.
but in the wellbore, it's something else.
No, sigma 3 in the far field can be one of the in situ stresses.
Yeah.
If I'm near the wellbore, it might be another kind of stress that we are going to learn later,
Yeah,
a
I know
cylindrical
that.
stress, yeah. But by sigma 3, and actually this is a very good point because I remember in my proposal of my PhD, I had like sigma ZZ, for instance, the axial stress or some weird stresses that we are going to learn later on in this module. And smaller than minus T,
Yeah.
right? And one of my a Chinese professor, he told me change that to sigma 3 so that you are more general.
Yeah, I see.
Because sigma 3 is like you are saying the most tensile of all exceeds. If one of the stresses exceeds, it would be the most tensile, right? It will exceed before the others.
Yeah, for any regime.
Yeah. And it is universally sort of applicable, yeah. That's why he told me change it to sigma 3 to be on the safe side. And he's right. The magnitude of T can be measured in the laboratory for rocks using the Brazilian. You know why they call it the Brazilian test? Because it was invented by a Brazilian guy. Yeah. If you invent a test, they're going to call it. Yeah.
Like very short.
They're going to call it the Algerian test if you guys invent something.
I came waiting for you.
Argentine blowout.
Anyway, the Brazilian test is very simple. It was a guy from Brazil, Carneiros is his last name. He came up with it, I want to say when he was 29 years old, something like that. And it's a smart way of basically, okay, I have these machines in the lab. We're gonna see it. Let me show you the picture. There you go. Okay, we have these machines in the lab. This is from the lab I used to work on in Texas. They basically have a plate and a point load on the top. You put something inside and you make the plate move up slowly until you can feel it. Now, if the plate moves up, what you get, by the way, it's bulletproof glass that I have inside that in the picture. PMMA, plexiglass. So this moves up. Newton's third law of motion. So I have compression loads applied at the top and bottom of the material, right? What do I have on the sides of the material?
Atmospheric pressure.
No, yeah, but what do I have here on the sides? Tension. When will the material fail first? In tension or compression?
Tension.
In tension.
What do you mean?
It's easier to fail the material in tension than compression.
Yeah, like no. Depends on the, I understand what you mean.
So it's gonna fail first in
Okay.
tension.
Yeah.
So you apply compression and you force it to fail in tension.
No, you are creating intention in the border.
Yeah, indirectly.
Yeah.
So when it fails, let me use a different color. Do you want white? Yeah, so it's gonna fail like this, 90 degrees in tension. So you apply compression because this machine is good for compression, and the rock samples are easier to apply compression on them. But it's gonna fail in tension because of the indirect nature of because you apply compression, but you get tension this way.
Yeah.
That's why this Brazilian guy was very smart. He thought about it in a different way.
And then how you measure the tension force?
Oh, we're gonna see. Oh. You measure the compression you apply, you plug it into this equation, and you get the T. Yeah. Because, a cylindrical sample, you use length R, length L, radius R, is used taking advantage of the cylindrical shape to create tensile stresses with application of a compressive force along the sample's diameter, that's the top down, and then you break it right and left, right? So a solution of the stress state within the sample, assuming a linearly elastic homogeneous material, yields the magnitude of T. So I measure how many pounds of force in compression do I need to fail? So this is pound force, right?
But I think this is for cylindrical shape, right?
Yeah, it's cylinder.
But you did it.
Not cylinder? How is it?
No,
It's
it's
like that?
cylinder like this.
Okay.
Yeah.
If you would do it like this, you will not get
Yes.
yeah, you will
Like-
not get tension like.
No.
No, I mean, it will not divide by PRR.
It's cylindrical, but
Yeah, because the PRR is the surface that is perpendicular to the tension point.
Pi.
Yeah, because you know your F measurement is 2F.
Yeah. It's
Yeah, so
2F.
so it's
So you have 2R.
so it's 2F divided by 2 PRR. So you take 2 by 2 and it's
and you
your F
can-
max.
Yeah, that's how he did it actually. I have a picture of
you
it.
know what involves here much is the surface of applied pressure.
Yeah. And you assume that it's point loads, but
Yeah.
it's never always point loads.
Because if you will do it like if you put your samples as vertical, you will not get tension. you will get
No.
friction.
No,
You will divide.
shear failure.
Even you will divide by PRR.
We're gonna talk about this in the UCS testing.
Yeah.
Note that the combined stress with compression in the direction of the compressive stress load and tension in the direction perpendicular to the stress load along the diameter is what the arrows are showing. I'm applying compression top down and I'm getting tension left and right. Okay, and then I just plug. So this pound force value is the value at which I fail. So it's the value at which I get the T, basically. It's very easy to do in the lab. And if we were,
Yeah, because you have tension on the cylindrical shape.
Yeah, but it should be PRR.
uh,
PR and R.
this is the article.
Yeah, to be.
But the P is diameter.
Yeah.
2R. That's the guy. He was born in 1913. He died
Mr.
in.
Brazilian guy.
Yeah. What year did the article come out?
2001?
No, 2001 he died.
Oh, okay.
I think he was 29 when he did it.
Volume April 22, no, was the volume.
In the 60s. It was 30s and 60s. In 1968, he got a sabbatical to go to France. And no, 47, 31 years old. Or no, 34. No, 47, he was born in 13. So if he invented it in 47, He was my age when he bought it.
Ooh,
Sounds like.
of competition.
Yeah. Oh, the method was presented in September 1943. So
This paper came out around those years.
43. Yeah, he was 30. I remember the 31. I remember I was telling the class last year that he was 31 years old when he got it. But maybe I read it from another article. But anyway, this is the guy. I don't know why. Carneiro is not a very hard to pronounce name. I don't know why they call it Brazilian. It's,
Maybe it's like more, like more country water, something like that.
I think it was like, oh, we do the test that the Brazilians are doing, you know, it was like, it became like that, no, they were like, oh, the
maybe,
Brazilians. Yeah.
But it's still valid, right?
Yeah, yeah.
Yeah.
We used to, when I was taking geomechanics myself in class, we had five labs, and I was a TA after that. And one of the labs was Brazilian. Then actually it's very easy, very quick. You just need to get one reading. Well, you need to measure the diameter, you need to measure the length.
You caliper.
Yeah, but those are standard, like, then measure the, very quick.
And
Very
the flow goes with 0.5 PSI per MPa, something like that.
Yeah, it depends on what units you want to measure. It- Very, very
It's
easy.
not the norm, 0.5.
0.5.
PI per minute, something like that for this test.
Oh, it doesn't matter as long, I think there is a limit to, was it 0.0002 inches a minute, something like
Yeah, the
that?
piston movement.
So
by
2
the-
inches is like 5 centimeters,
Yeah, exactly.
right? So we had a, but it depends on what kind of loading frame you are using, we have specifications. And the loading frame that we had at Texas, it was a Humboldt brand. It had 10,000 PSI,
I saw it
10,000 pounds.
I saw it at the R&D department of Sonatra, I think. They use this stuff.
Right. So a quick example problem to finish today's class. Determine the tensile strength of the shale sample that displayed a peak load of 470-pound force. The sample diameter is 1 inch and the length is also 1 inch. So it's a pretty short. Oh yeah, it was short samples. I remember them.
Yeah.
We had to put them in the oven to dry them before the class. And then if somebody, we put them on the desk and we went to them anything, so if somebody grabs it, like it was feeling hot on there. It wasn't burning them, but they had to be dry, basically. So we use that equation. I put the numbers. And why do I put 0.5 and not 1? Because I was given the diameter. Diameter is 2 times the radius. So I put R is half inch, right?
Yeah, so it's
What
like
you were saying to P?
940.
If it's 2P, it's
Because
it's diameter.
it should be 2PRR. Plus, you see, it's 2PR, and then this is the section divided by L, the thickness.
Yeah.
Next, the thickness of the
There you go. It's like this, and then this becomes D.
P.
And that's what the guy had in his. And that's what the guy had in his
You will see one side.
article. No.
You see the pressure. You see the pressure in the force over
There you go.
is force over surface.
Yes.
So the force, the surface is yeah. So the force is perpendicular on what surface? On this surface, on the wall. The wall is the perimeter of this section times
Yes.
L. What's the perimeter? 2PR.
2PR, yes.
Yeah, that's why 2PR times L.
Yeah.
But
P
then,
is diameter.
but then you have
Yeah, P is diameter.
yes. But we don't see two in the relationship
It cancels
because
out.
it has to be two forces, 2F.
Is it because
It's two forces. It's force from up and force from down. It's two
Newton's
F.
third law. You
yeah,
apply.
we have two forces?
Yes. And then when we subdivide 2 by 2, we will have P over PRF only. Can you go to the next slide?
Yeah.
Next, yes.
There you go.
It should be 2F over 2PRR, and then 2 goes with it.
But we have only, we're assuming only, look, there is only one F.
Yeah,
That
but
is-
Yeah, because you only
it's
apply
easy.
one.
Yeah, they are applying on one.
No, but you are measuring this, but this by Newton is this and this.
You apply the same.
Same, not the
So
F.
it's 2P,
2P, yes.
yes. It's 2F max.
Yep.
Yeah, so it's 2F max over
It
this.
goes with the,
Yeah,
yeah.
those with-
I thought that
Yeah.
you were talking about something else, you know, and okay, no.
I mean, you apply only one, only the force.
You measure only
You
one.
get the other
Physically
one.
it's two.
Yeah.
I was thinking that he was talking about volumes.
No,
Not
no.
like how it.
It's a very simple test, actually, very.
Yeah, but physically, you should, when you see PRR, it
He
has
needs
to be
the
2P.
demonstration, he wants the demonstration.
Yeah.
No, I want just to emphasize that why these two goes. Now, you don't take it by heart, just take it physically.
Yeah,
It's very simple.
It's very simple, exactly.
yeah.
Expression.
I understand it, but I was like, what's going on?
And this is the value that,
He's talking about what I was thinking.
oh, this is a value typical to what you see for gypsum. Like, if you use a gypsum sample of 1 inch diameter and 1 inch length, you would expect the failure to be around 500-pound force between 400 and 500. Not that bad. Anyway, have a meeting with Kalu, so I will end the class today, and then we'll carry on Friday. Thank you very much. I will see you on Friday. Stop recording.